right, so let's continue where we left off. We were talking about hybridized orbitals. So we're just going to kind of revisit where we left off here for hybridized orbitals. So these orbitals, and we're specifically talking sp. So the ones that we're going to talk about are going to be sp2 hybridized orbitals. There's sp3, sp3d, and sp3d2 hybridized orbitals. So for S and P hybridized orbitals, right? S is one orbital, P there's another orbital, but this is two orbitals. So from our energy level, we have an sp orbital here, and then we have, so this is our P, this is our S. If we place two electrons in here, now two electrons, because this is an sp orbital, 1, 2, there should be two electrons here. This one here is going to enter this orbital, and they create two sp hybridized orbitals. Right? So these two electrons here combine with this, and we get two sp hybridized orbitals. But we're also going to have two unhybridized orbitals. So when this happens, is that we gain two sp orbitals, but then we have two unhybridized orbitals. So these sp orbitals, when they bond, see if I have an image here. Nope, not yet. We'll talk about bonding and shouldn't. This is sp3. sp or they break this up. So when we're looking at sp orbitals here, is that the sp orbitals are going to make some sigma bond. We know what sigma bonds are, right? We have some s subshell overlapping another s subshell. We create a sigma bond. When pi bonds meet, when they meet end on end, not this way, but when they meet end on end, we create more sigma bonds there. So these sp orbitals are going to create, at one point, the atom is going to create two of these bonds, two sigma bonds here. But the unhybridized orbitals that are available, are able to create pi bonds that we're going to see. So this is just one type here. The other type is what we're going to call sp2 hybridized orbitals. So if you're ever lost on how many degenerate orbitals we have, because these two orbitals here are the same energy level, we get two hybridized degenerate orbitals. So here, sp2, well, this means that we're going to use two of the pi orbitals, or the p orbitals, I'm sorry, two of the p orbitals. And when they're rearranged, so this is our sp hybridization, right? We have an overlap here, and we create these orbitals with this small area of electron density, but a large area of electron density. So these combine here in these three areas, and we get something that's considered sp2 hybridized. But this is going to require three electrons, right? Is that now this one here will jump here, and two of these p orbitals, and we create three. So 1, 2, 3. We're going to create three hybridized orbitals that are sp2, and now only one is going to be unhybridized. And then if we look at, and these are just some different types of elements, because anything that's unhybridized is going to give us this trigonoplanar geometry here. Whether there's a double bond, whether there's no double bond here, is that sp2 will give us some type of trigonoplanar here, right? We learned yesterday in the lab that this is going to be trigonoplanar, the electron geometry, and here the molecular geometry is trigonoplanar. This end here, trigonoplanar. This end here, trigonoplanar. And for the SP, did they give us any? No, they don't give us any examples for that one.
You said the unhybridized will make this?
The sp2 hybridized orbitals will make this geometry. The sp ones are going to make something very linear, and we'll see that in a couple of, or in one of the examples that I have later on. But this is going to make something linear. These will make something that's trigonoplanar, and the sp3 is going to make something that's tetrahedral. So the sp3 is going to be 4 hybridized orbitals. So here we have our 4 electrons. This electron's going to jump over here, and we will create 4 hybridized orbitals. But at this point, there's no more unhybridized p orbitals. So we have 4 degenerate sp3 orbitals here. Each one of these will be making a sigma bond, right? In order to make a pi bond, we need to have some p orbital up here that's been unhybridized in order to make one of those pi bonds. And here we see it. So here we have this p orbital here, but it's head-on, so we have a sigma bond here, sigma bond here, sigma bond here, sigma bond here. So this atom here is creating 4 sigma bonds that are all sp3 hybridized.
I noticed SP only has 1 electron, but it's only going in one direction. Is that always going to be the situation, or will we have a situation where S and P goes the opposite direction?
So when we create these let's take a look here. So we have 3 or 4 sp3 orbitals. And they each have an electron going this way. So these are hybridized orbitals. And now when they make a bond, this sp3, these hybridized orbitals are going to make sigma bonds. So here, if we take a look, if we do this, am I able to do this?
No.
No. Why not? What do I have to do instead?
You have to do all of them.
Yes,
Once.
like this,
Sorry.
right? And then we can go ahead and do this. So kind of the same rule here when we get to the degenerate orbitals is that now that each one has one, this can now make a bond with another element that's going to bring an electron. And this one here, and if we take a look, right? Here we have something that's going to bond to it, something that's going to bond to it, something that's going to bond to it, creating those 4 sigma bonds there. So that's where the other electrons are going to come that have the other direction, is that they're made because we have some hydrogen that may come here, hydrogen that may come here, and that s orbital is going to overlap with this, creating those sigma bonds. Does that help answer a little bit?
Yeah.
Okay. So here we have what's considered SPD3. So this is going to give me 4 hybridized orbitals because we have originally this is the S subshell, this is the P subshell, the S and P subshell give us 4 orbitals, and we're always going to have these 4 orbitals. It's just a matter of how we hybridize them. If I only take if I only have these 2 electrons in the S subshell, we can only create 2 sp hybridized orbitals, and then 2 of them are going to remain empty, which are going to be some p orbitals. if we have sp3 or sp2, we're going to need 3 orbitals that are going to be hybridized, and one of the 4 is going to be unhybridized, that p orbital. Here, this gives us 4 orbitals, none of which are unhybridized. Here we still have those 4 unhybridized orbitals, but now we're bringing in some d orbital. So we'll have 5 hybridized orbitals because we are going to bring in an additional one. So if we're looking at sp3d2, how many hybridized orbitals are we going to get? How many? If we have 5 here, we're going to have 6 over here. All right? 2, 3, 4, 5, 6 hybridized orbitals, always beginning with just these 2 here. So this is going to be something very linear. This is going to be trigonal planar. This is going to be something that has a tetrahedral. sp3d. So when we're looking at these, we do have some examples. Like this is going to be octahedral. Right? Here's our central atom here, 1, 2, 3, 4, 5, 6 hybridized orbitals. When we get something that's sp3d2. We had trigonal bipyramidal, I think is what we called it here. So we have trigonal or bipyramid, I think is what it said there. In your textbook, but this is the one that looks like this. Here's our central atom. We have one out here, one out here, right? Giving us this structure here. So all of these hybridized orbitals are specific to some certain kind of electron geometry that we have here, right? Oh, it's not the right one. sp3d2. Right, the electron geometry here is not the molecular geometry, but the electron geometry here is trigonal bipyramidal, where we see that here, and these electrons are taking the place of one of those structures. So 1, 2, 3, 4, 5 hybridized orbitals. The same thing here. We have 2 electrons, or 2 lone pairs here, 1 lone pair, but we are having some explanation of these sp3d hybridized orbitals. Right? sp3 hybridized orbitals that can all make some type of sigma bond here. And then our sp3d2, which contains 6 hybridized orbitals, right? Each one of those making some sigma bond when we have something bonded to it. So here's a table as well that kind of helps explain this, and over here. So something with that we see sp is going to be linear, trigonal planar, tetrahedral, trigonal bipyramidal, and our octahedral here. So you're going to want to know this information for the exam.
Should we know the degrees for this as well?
The degrees, you are going to need to know the degrees. Yeah. So you'll need to know the degrees here for the electron configurations that we have. Not so much for the molecular geometries, but definitely for the electron geometries where we see those angles either going to be 90, 120, 105, or 180. So yes, I would definitely know those angles there. So just looking at this model here, right? What would the hybridization be for this?
Tetrahedral.
Tetrahedral, right? So this is definitely a tetrahedral. Now, what's the hybridization? Because that's the electron geometry. sp3, yeah. So these are all sp3 hybridized orbitals. And if we take a look at this one here, well, what's the hybridization here?
Selenium and
1, 2, 3, 4. There's 5 hybridized orbitals here.
So sp3d.
sp3d, yes. So this is sp3d. This one's not drawn particularly well. I'm going to redraw this, or Yeah, let's redraw this one here. I'm not a fan of how that's drawn. So we're going to take a look at two of the places here. Actually, maybe three here. So if we're taking a look at this component here, I'm going to put this in purple, just override it. If we're looking at this hybridization for the carbon here, what is the carbon? What are those hybridized orbitals?
SG2.
sp2, yeah, because this is trigonal planar here. This is trigonal planar, and the hybridization here is going to be sp2. Versus, let's see, 1, 2. Yeah, let me put this out just a little bit more here. And what would the hybridization be here? 1 hybridized orbital, 2 hybridized orbitals, 3 hybridized orbitals, 4 hybridized orbitals. sp3, that this is sp3 hybridization, while this one is sp2 hybridized orbitals, right? So just by the shape of it, we can tell what type of hybridization that's going to be, right? If we take a look at this one here, what's the hybridization? sp2, this is sp3. So you're able to recognize those hybridizations just by looking at that, what the electron geometry is for that specific element that we're looking at. So multiple bonds. Everything we're looking at, with the exception of the sp2, but let's understand this sp2 hybridized orbitals, right? So we know that one single bond is a sigma bond, double bonds is 1 sigma bond, 1 pi bond, and a triple bond is 1 sigma bond, 2 pi bonds. So when we have something that is sp here, this is our sp, this is sp, and then we have p. So in an sp2, there are 2 unhybridized p subshells. So when we're taking a look at that, 2 of them are unhybridized. I'm sorry, one of them, that's sp. One of them are unhybridized. sp, this is sp. Let me get sp2 in here. This is sp2, 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 and 1 hybridized. All right. Sorry, this is sp, this is sp2. So for here, for an sp2, there's 1 unhybridized p orbital. This is where we make our pi bonds. So if we're taking a look at something that's sp2, how many pi bonds can we make? Just 1. Because there's only 1 unhybridized p orbital. So we can make 1 pi bond. So if we can make a sigma bond and 1 pi bond, is that a double or triple bond? 1 sigma bond and 1 pi bond will make some double bond. So sp2 hybridized orbitals can make some double bond. Now if we take a look at, before we get to sp over here, let's take a look at sp3. How many unhybridized p orbitals are there? There's none. So if anything has an sp3 hybridized orbitals, can we make pi bonds? No, because we need an unhybridized p orbital to make those pi bonds. And all we have here, we just have 4 sigma bonds that are going to occur. So anything that says sp3 hybridized orbitals is not going to make a double bond. Is that we need unhybridized, which means here we can create pi bonds, and here we can create pi bonds. So anything that's sp, if sp2 can only make 1 pi bond, but sp can make how many pi bonds? 2, because 2 of them are unhybridized. So our triple bonds are going to occur, we're going to have 2 pi bonds and then 1 sigma bond occur, and that will be their difference there, making double and triple bonds. So I think there's a overlap here. So this is what we have here. So we make this 1 sigma bond. So when we have, let me draw that structure that they had there. So this will always make the sigma bond first. So here is our sigma bond. But since this is sp2 hybridized, there is an unhybridized p orbital here. So this is 1 sigma bond here, but then the way that these are oriented here, remember that that is how we make our pi bond. This, I hate making these dumbbells. Right? Does this create a pi bond? This is a sigma bond. The only time that we can create a pi bond is when we get this overlap twice from the orbitals being side by side versus head on and head on, right? Is that this creates pi. This overlap here is just simply a sigma bond. So we create 1 pi bond here. So these 2 will meet and we will create 1 pi bond. Here's our sigma bond and here's our pi bond, and this gives us now some double bond. So now we're talking sp. Well, here's our original sigma bond. But with 2 unhybridized p orbitals, well, this is going to create a pi bond using one of the unhybridized orbitals, and this will create another pi bond using one of the other unhybridized orbitals, giving us some triple bond. So our triple bond is viewed that way. So here it is here, where we have these unhybridized p orbitals. Here's the overlap, or for the sigma bond. So these 2 here will create some pi bond, and then these 2 here will also create a second pi bond, giving us some structure here that has some triple bond here. And then just kind of revisit, I did introduce resonance structures. So these here are what we consider resonance structures. What happens with resonance structures is sometimes these electrons move around. So here we have this orientation here, but what can happen is that this electron here decides to move here. This one decides to move here, this one decides to move here, and it gives us a different orientation on those double bonds. So these two would be considered resonance structures. The number of carbons remains the same. The number of hydrogens, the number of electrons, the number of double bonds are the same. Nothing has changed except the location of these double bonds. So we have some, what we consider a resonance structure here. Here we see another resonance structure. Is that what changed is this negative charge is now on this structure, or on this oxygen, right? And we get over here, and then a double bond is created here versus over here. So we have a bunch of just what we consider to be resonance structures. I think CO2 is always a good one for resonance structures. This is one way to draw CO2. But this isn't the only way to draw CO2. As we could draw it this way as well. Instead of having a double bond here, maybe we put a triple bond over here, and then we give this one a single bond. So this is another way that we can, so these are what we consider resonance structures over here. Is that this is a resonance, here, the total number of electrons here, question or stretching?
Yeah, which structure is more stable?
So we determine that by what we call formal charge. Let me draw one more structure over here. I think that we can draw one more structure. But here we have 2, 4, 6, 8 electrons, 16 electrons. This still has 16 electrons. Is that there's 8 over here, there's 8 over here. The number of electrons haven't changed. Let's see, what else could we do with this? Would this work here? 2, 4, 6, 8, 2, 4, 6, 8, 10, 12. No, that's too many here. Oh, you know what we can do? We can do this. A resonance structure here. Alright, so this is more than just me flipping it around, is that this is considered a resonance structure here. So, how we do that is we have to calculate formal charge. So I'm going to write the formula for formal charge. Make sure that you do have it because you are going to be calculating formal charges on the homework, formal charges on the exam. But in order to calculate formal charge, you're going to take the element valence electrons, and you're going to subtract the lone pair electrons, and then you're going to subtract 1/2 subtract 1/2 of the bonding electrons. So you take the number of the element's valence electrons, you subtract the lone pair electrons, and you subtract half the bonding electrons. So let's calculate the formal charge here. How many valence electrons does oxygen have? It's in group 6.
6.
So 6 valence electrons. Minus how many lone, not lone pairs, but how many lone pair electrons?
4.
4. Minus half of the bonding electrons. So here's 2, that's 4, but we just need half of them. And that equals 0. So the formal charge on this oxygen is 0. Carbon, 4 valence electrons. There are 0 lone pair electrons. 2, 4, 6, 8, but we only need half of them, and that is also equal to 0. This oxygen is identical to this oxygen. We don't need to calculate it. It's 0. Let's calculate this one. So somebody tell me the formal charge of what this is. -1. So 6 valence electrons minus 6 lone pair electrons minus half the bonding ones, which is -1. And then this carbon is going to be 0. And then the oxygen would be
Positive one?
and because this one looks like this, we can just say, well, this is +1. We know that carbon is just going to be 0, and then this is just going to be negative. The more formal charges we can get to 0, the more stable it becomes. And we know that oxygen is pretty electronegative. Do you think it's stable for oxygen to have some positive formal charge? If it's an electronegative atom, not very stable, right? But it is a structure that we can use. This is a legitimate resonance structure. It's just not a stable structure. But that's how we determine which one is going to be more stable, is the more zeros that we can put on it, well, that's going to be the more stable structure. We had another one. I'm going to erase this here. So this one came up in your lab as well. So we have this bare bone structure here. This is going to be 5 plus 3 plus 24 gives us 32 electrons. This is one of the structures of phosphate. But it's not the only structure that we can build. We can also build, well, I'm going to redraw this structure here. And we're going to make an adjustment to this one here. All right. So this isn't the only way that we can draw it. It's because phosphorus is hypervalent, it can take more electrons, more than just 8. Is maybe we share these electrons with phosphorus. And now let's take a look at the stability of this. So here, what is the formal charge on phosphorus? Group number 5.
5. Oh, sorry.
So this is in group 5, so what's the formal charge?
Positive 1.
Positive 1. And what's the formal charge on oxygen? Oxygen's group 6. -1. So this is going to be minus, this will be minus, this will be minus. Because I already know what those look like, I don't have to determine what these are. This is minus, this is minus, this is minus. But now I have to adjust these. So now what is the formal charge on oxygen? 0. What's the formal charge on phosphorus?
0.
0. Right? Which one is more stable?
Option number 2.
Option number 2 is a little bit more stable, right? Because we got 2 of these atoms or elements here to have 0 formal charge here. But again, these are what we consider to be resonance structures, right? Is that they both contain the same number of atoms, the same charge, overall charge. And that brings us to, I think we're ahead of schedule. I shouldn't have rushed so much. I thought maybe I rushed. All right. Gets us to molecular orbital theory. So we've talked about valence bond theory. We've talked about hybridized orbitals. Now we get to MO theory, molecular orbital theory. So we have to think in terms of wave functions. This is kind of an early on quantum mechanic idea when we consider molecular orbital theory, but it is an approach from quantum mechanics here. But when we remember talking about waves, we talked about constructive waves and destructive. Right? Constructive waves add to the wave. these are in phase. So if I take this wave and this wave, and notice how they're both in sync here, is that this is constructive and it will add to the overall wave. Well, these are out of phase. And if we put these here, this is destructive. And we just get some node, right? Because this is interfering with this is interfering with this, and we just get some node here. Well, atomic orbitals behave the same way. Is that we can add to the electron density, or we can have no electron density. We can have, and these are what we consider to be bonding and anti-bonding orbitals. So here we have two atomic orbitals, both some s orbitals here, and we have our overlap, our sigma bond here. And this sigma bond, if we do it constructively, is that here we get what we're going to call a bonding orbital. And then at the same time, we get what we consider to be anti-bonding orbitals. But they are designated with this symbol here, sigma, and it's sigma because this is a sigma bond. So this is a sigma s bonding orbital. And the anti-bonding is always marked with this little asterisk. So we know, because we are going to be drawing some molecular orbitals, and this is how we tell the difference between our anti-bonding and our bonding orbitals, is just by simply using this little asterisk to define those. So if we add this and this, if these two meet up, we can see that this is going to cause some large area of bonding, some for electron density here. So this is constructive, and we have our bonding orbital, right? This is a bonding p, right? Because this is a p orbital, this is a p orbital, but end on end, it is sigma, right? So this is our sigma px bonding orbital. And this denotes anti-bonding, right? Is that these orbitals are different, and we're going to have some anti-bonding orbital here. But again, it's still sigma because they're head-on. Then we get our pi orbitals, right? These are in sync here, the way that they're oriented. It's going to be constructive, and we get our bonding pi p orbital. And then we also get an anti-bonding pi p orbital. So when we're looking, all right, so let's take a look at helium now. No, hydrogen. So hydrogen, if we wanted to do the electron configuration for not just hydrogen, but H2, well, we have the sigma 1s over here, so let's put sigma 1s, and there are 2 electrons there. And then we go to the anti-bonding one, and there doesn't happen to be any in the anti-bonding. So this would be our electron configuration with regards to this molecule, not just hydrogen, but the electron configuration for the molecule. Something else comes to mind with this, is something that we call bond order. For bond order, we take the bonding electrons, minus the anti-bonding electrons, and we divide that number by 2. And that gives us something that we call bond order. So in this structure here, how many bonding electrons do we have? 2. And how many anti-bonding electrons do we have?
No.
None. And if we divide that by 2, that equals 1, right? Don't get your calculators out. Well, if we look at hydrogen, how many bonds does it have? 1. Not bad. Let's do we're going to do N2. Shouldn't have written that so big over there. So with N2, we're not going to include the 1s. We're just going to start at the 2s. So for the 2s, we have to take care of, we have 2s, and we also have 2p, and this is where our pi orbitals are going to come in from. So we're going to have, this is going to be our sigma 2s. Then we're going to have our anti-sigma 2s. And then we're going to have the p subshell gets 3 orbitals. One of them are going to be sigma, right? And the other ones are going to be pi orbitals. So here we have the, we're going to have, sigma p. And then we're going to have, we're going to repeat this, and we're going to have, these are anti-bonding, these are anti-bonding, and this is also an anti-bonding p orbital. Don't worry about px, pz, py. As long as I'm good as long as you get that there are 2. This here. This represents the bonding p orbitals, and this represents the anti-bonding p orbitals. So you have bonding and anti-bonding p orbitals. So as far as nitrogen goes, N2, how many electrons does N2 have? This is in group number 5. Rhymes with N. How many electrons?
10.
10, perfect, here we go, thank you. So there's 10 electrons here. So let's put 10 electrons here. We're going to follow Hund's rule. So here's 1 electron, here's another electron, 2, 3, 4, 5, 6, 7, 8, 9, 10. Now, this would be the molecular or the molecular orbital structure for nitrogen, for N2. Now let's calculate bond order. Bond order. Remember how to calculate bond order? We take the bonding electrons minus the anti-bond electrons and then divide that number by 2. So how many bonding electrons do we see here?
4.
Sorry.
Are these bonding or anti-bonding? So how many bonding electrons are there?
8.
8. How many anti-bonding electrons are there?
2.
2. And we divide this by 2, and what is our bond order?
3.
3. So 3 is the bond order. So how many bonds should N2 get? 3. Yeah, exactly. So when we draw N2, this is N2, 10 electrons. 2, 4, 6, 8, 10 electrons, and with a bond order of 3. So it matches our molecular orbital theory. Right? When we draw the Lewis structure, this is how we draw our Lewis structure. 2, 4, 6, 8. Oh, not even about 2, 4, 6, 8, 10, 12, 4. That's way too many. All right? Yeah. Is that when we draw the Lewis structure, we know that at this point, well, we better start sharing electrons. We're going to take these and share them. We're going to take these and share them. And we come up with our Lewis structure. And this matches just what our molecular orbital theory says.
Does that also identify like the formal charge?
No, it doesn't identify. No, formal charge and bond order are different. So it does not identify the formal charge on it. No. I'm going to keep this one up. I'm going to erase some things here. Instead of N2, you do have to memorize how to draw these. On the exam, you will have to draw molecular orbitals. And I want you to point something out here. Is that the energy changes as we go from left to right. And we're not going to go beyond neon. We're going to stick with this. Beyond neon, these get more complex. Right? So we don't want to complicate this too much. We are only going to be doing molecular orbitals from lithium to neon in that second energy level. Okay, so 2s, 2p is that's what we're going to focus on. But notice what happens to the energy of the orbitals here. This sigma p orbital tends to drop in energy, right? And a lot, right? These kind of go down slightly. They go down in energy because they're becoming more stable, and neon is the most stable. So as we lower energy, they become more stable here. But look what happens to this orbital here. So this orbital, right at nitrogen and oxygen, it drops below those pi orbitals. So this is sigma, sigma, pi, sigma, pi, pi, sigma. These are anti-bonding. These are bonding orbitals over here. But this bonding orbital drops dramatically going from nitrogen to oxygen. So you do have to know how to draw and what that break point is. So anything from lithium to nitrogen will look like this. From oxygen to neon, there's a change here. And we notice that change right in here. So this is sigma 2s. This is the anti-sigma 2s. This is going to be our sigma p. This is our pi p orbital, pi p orbital. Oh, we should put 2p, 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 2p. This should all be 2p here. And then these are going to be our anti-bonding 2p, anti-bonding 2p, and anti-bonding sigma 2p. But we see the change here, lithium to nitrogen, and then oxygen to neon. If you don't remember that, cross your fingers and hope you get the right one. Okay? So if we do 2, O2. So now let's do O2. Oxygen is in group 6. How many electrons do we need for O2? 12. So we need 12 electrons. So let's start putting these electrons in here. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Hund's rule, right? Remember, I didn't put it in the same one. I did separate them so that each one of these get that. And now let's calculate bond order. So remember which ones are your anti-bonding. Right? How many bonding electrons do we have?
All the way to 26.
8. 2, 4, 6, 8 bonding electrons. And how many anti-bonding electrons do we have? 4. So 1, 2, 3, 4. We're going to divide that by 2. What is the bond order? 2. So our bond order is 2, which means how many bonds does O2 have? So oxygen has 2 bonds. But yeah, we definitely see that pattern mixing, and you do have to know which one to draw. Is that we see that, just that sigma, right? That sigma p orbital there just drop in energy. All right. That is chapter 5. So yeah, we finished a little bit early. I think we're still okay. What are we starting next? Compound. All right, so starting next week for chapter 6, we'll start getting into some calculations. Finally, like we've been introduced, we've taken 5 weeks to just be familiar with atoms, with electrons, with how to put things together, with how to name them, that we're finally at the point where we're going to start making some calculations, some math involving concentrations, involving masses, involving stoichiometry, involving, just different chemical reactions. I'm a fan of this book here. I don't know what some of the other instructors, they throw you into the calculations and then later on they explain the elements in the periodic table, and I don't agree with that textbook. I think we need a foundation of understanding, how things bond in the first place, and then we can finally move on to understanding some calculations regarding chemical reactions. So we're good for today. You guys can just leave a little bit early. I'm going to hang out if you have any questions. If you don't have any questions, for tomorrow, I am looking at your lab books tomorrow. If you have not written the lab report portion in there, your data tables, your procedure, I will ask you to leave the lab tomorrow, okay? Tomorrow's a wet experiment. We did have a little break where I didn't check because we were doing dry labs. But tomorrow's a wet lab. Procedure, MSDS, data tables, everywhere you're going to record your data. We're doing lab 8 tomorrow, yes. So lab 8 tomorrow, manganese. Please make sure that it is in your lab notebook. If it is not, and I don't mean write it when you get here. Like, needs to be done. If it's when I check it and it's not written in your lab notebook, sorry, but you can't stay for the lab.
I just be prepared.
Be prepared, yes. Be prepared. Goggles, lab coat, proper dress attire. All right? Yep, no problem. We'll see everybody later.